In this video, I am going to give you all of the drawings for all of the geometries that I would like you to be able to recreate with actual molecules. There will be some additional footage where we look at models. This might be in a Zoom session that you attend live, or I may be able to get some videos up on YouTube or find you some simulations. But either way, we will get you something beyond what's on this flat paper. But since we communicate everything through flat paper and flat screens, it's important to be able to recreate these in that manner. So starting out with steric number equal to 2. This was our linear geometry. And so steric number equals to 2. The central atom has 2 things attached to it. And we are only going to look at the situation where our generic central atom A has 2 atoms attached to it. We're going to make those B generic atoms. And so the farthest apart that 2 things can get in 3D space is 180 degrees. So the bond angle in a linear shape is 180 degrees, and that's it. So if I had something with a steric number of 2, but a coordination number of 1, so if one of these B atoms was replaced by a lone pair, I would just have a diatomic molecule. So we don't talk about that as a possibility when we're doing our VSEPR geometries. Now we will see it for all of our other ones. So that's it for steric number 2. Should probably just put a line here. Steric number 3. Our basis, our electron geometry is trigonal planar. So anything that has a steric number of 3 and a coordination number of 3. So A in the middle and then 3 B's attached to it. The farthest apart that 3 things can get in 3D space is 120 degrees, all in the same plane. So this is why this one is called trigonal planar. And every single one of these bond angles here is 120 degrees. Okay. So if our steric number is 3, but our coordination number is 2, so same shape to start out with, but one of my B atoms happens to be a lone pair. And just because of how I have this space, I'm going to put my lone pair in the top position. It could be in any one of the positions though. And then my other 2, B and B. Now I start out with a 120 degree bond angle between these 2 B atoms, but because of my repulsion order, right, this lone pair is repelling the bonding pair more than when it was a bonding pair, and it's repelling more on this other side. So my bond angle in the steric number 3, coordination number 2 is going to be less than 120 degrees. And the exact angle is going to depend on the identity of the atoms. We do have a different name for this one. So the name of this shape is bent. And that is it for steric number 3. Let's get a dividing line here. So up next is steric number 4. And the electron geometry here is tetrahedral. So if I have 4 things attached to a central atom, and they are as far apart as they could possibly be in 3D space, that ends up being 109.5 degrees apart. So one of the ways that we represent this tetrahedral shape is by showing 2 bonds that are in the plane of the paper, right? And so this angle here, since I'm going to make a perfectly tetrahedral, this is a 109.5 degree angle. So when you're drawing this, you should be really careful to make sure, let me make sure that my drawing looks this way, that it looks like it's more than 90 and less than 120. So the other two, remember, we're trying to put them as far apart in 3D space. So one of the other attached atoms comes out of the plane of the paper, and we use this shaded in wedge to show that it's coming out of the paper, or out of the screen in this case. And then we use these dashes to show that this other one is going back behind the plane of the paper. And every single one of these angles is 109.5 degrees. All right. An important thing to note about this dashed line, please do not make your dashes look like this, because this actually means that it's a partial bond. So they should be, I guess, not end-to-end dashes. They need to be these parallel dashes that I've shown. All right, 4 things. Tetrahedral, 109.5 degrees apart. If we replace one of these atoms with a lone pair, so we have a steric number of 4 and a coordination number of 3, what this looks like, and again, I'm going to put my lone pair on the top just because of how I have this drawn in here to save space. And then that leaves me with one bond in the plane of the paper. I still have one coming out and one going back. The basis for my angles was 109.5. So these angles are now less than 109.5 because of the repulsion order. Right? This angle's also less than 109.5. The angle between this B and this one going across the back is the same. And the name of this shape is trigonal pyramidal. So if you look at the overall shape of the molecule, where the lone pair has contributed to this shape, but we're not kind of going around it, it looks like a little pyramid with a triangle bottom. And I do have a specific example here for you. So you should find, and maybe this looks familiar from when we were doing Lewis structures, right? When you did the Lewis structure for NH3, it had a lone pair on the central atom and then 3 bonds. So nitrogen had a steric number of 4, but a coordination number of 3. If we drew this as a VSEPR geometry, it would be trigonal pyramidal. And it might be one of the examples, but I'm sure it comes up in a practice problem. And if not, you have the skills to put this together. The bond angle in NH3 is 107 degrees. So you can see it's squished, but just by a little bit. So about 2 degrees in NH3. One more for steric number 4. And that's if we have a coordination number of 2. And so what this would look like, my central atom, I'll still replace that top one, and then I'm going to replace my bond that's going back behind the paper with a lone pair. That leaves me this bond in the plane of the paper and one coming out. And the name of this shape is bent. And the bond angle here, I have 2 lone pairs squishing down this bond angle. It's going to be even smaller than 109.5. And based on the Lewis structures that we have done so far, you might see that this looks a lot like the Lewis structure for H2O. And in H2O, oxygen has a steric number of 4, coordination number of 2, and the bond angles end up being 102 degrees. Okay, so something, I didn't address it with the steric number of 3, but in every single case, you'll notice that I put the lone pairs directly on the central atom, and I didn't leave that line in the picture showing the basis for the geometry from which it came. And the reason that we don't do that is because that single line represents a bond that has 2 electrons in it. So if we were to draw something, I'm going to put this in gray, and then I'm going to put a big red X through it because this is not what I want you to do. If we were to do something like a line with a lone pair and then my B atoms attached, it's really tempting. It helps you visualize that geometry maybe a lot more easily. However, it looks like we have a bond to a lone pair, which would technically be 4 electrons, but there are only 2 electrons there. So please don't do this. If you still need some assistance in visualizing these in 3D, I can recommend some model kits so that you can build them and kind of put your hands on them and turn them around and see what these shapes look like. But when we draw the actual pictures, just put the lone pairs in. You have to use your imagination and visual skills to picture how these sit in 3D. Which means we're really used to drawing water as something like this, where those 2 bonds are in the plane of the paper, and then we just stick the lone pairs on there. But what's underlying this that you have to remember, and that will be really important when we talk about bonding things, is that we have one lone pair coming out of the screen at you and one lone pair going back behind the screen or behind the paper, because these 4 things still need to be as far apart as possible in 3D space. All right, that's steric number 4. So let's do steric number 5. And this is where we get to apply Bent's rule finally. So steric number 5 is trigonal bipyramidal. And the farthest apart that 5 things can get in 3D space looks like this. I have a central atom. I have 1 bond going straight up and 1 bond coming straight down. This in the orientation that I've drawn it. So those 2 bonds are 180 degrees apart, but in between them, kind of around the middle, maybe kind of similar to what our DZ squared orbital looked like, I have this center set of bonds. 1 going back, 1 coming out, and with how I've drawn it, 1 in the plane of the paper. And the bond angles here, the angle between this one pointing up and the 3 in the middle is 90 degrees. The angle between the bottom one and all of the stuff in the middle is 90 degrees. And around the middle, these bond angles are 120 degrees. So I have different bond angles, and hopefully it explains why I've not yet drawn in the atoms that are attached to these positions. Instead of using B, I'm going to use S for my small atoms, and I'm going to use L for my large atoms. So if I'm a small atom, I could fit in any place. So let's not start with the small. If I'm a large atom and I go into one of these positions at the top or the bottom, I have pretty crowded stuff around me. I have 3 things that are 90 degrees away. So if I'm a large atom and I have the opportunity to go somewhere where my neighbors are mostly 120 degrees away, they're still close to the other things. There's more space in these positions around the middle that kind of looks like the equator, perhaps. And there's less space in these positions that look like, I don't know, maybe an axis for spinning around my equator. So my small atoms I've put in axial positions because they look like, say, the axis of the Earth, and then these large atoms are in equatorial, which are around, say, the equator of my molecule. Okay, so that's steric number 5, trigonal bipyramidal. If I replace one of those atoms with a lone pair, so steric number 5, coordination number 4, the lone pair is considered large. It has to go in an equatorial position. So in my generic atom, put my lone pair, say, here in this equatorial position. What I'm left with are my 2 axial and my 2 equatorial. Now I'm going to go to just generic B atoms here. It looks a little weird, but my bond angles here, right, it's a little less than 120 because that lone pair is going to squish stuff. It might squish these down a little bit as well, but not as much. And the name of this shape is called seesaw. And the reason it's called seesaw is because if you were to take this and tip it over, so we could rotate this picture in space. And if I do that, it looks like a seesaw that you might see on the playground. I can still keep replacing some of these atoms with lone pairs. So steric number 5, coordination number 3, lone pairs are still going to go in those equatorial positions because they take up more space. So I've used up that spot, take up this equatorial position in the back. So I'm left with my 2 axial positions, and then with how I've started drawing it, I still have an atom in this equatorial position that's coming out of the paper. If I were to do a little rotation here, so this is my please rotate arrow, I could rotate it so that that equatorial B atom is the one that's in the plane of the paper. And so what I'm left with is this. I still have my lone pairs in equatorial positions. If I were to tip this over, say, tip it over down to the left, or if you turn your head with how it's written, it looks like a sideways letter T. So this is called T-shaped. I have one more for steric number 5. Thankfully, this one is pretty straightforward. Steric number 5, coordination number 2. So I have 3 lone pairs. They all go around the middle. And this shape looks like where we started way back at the beginning of this video. This is a linear shape. One more steric number to go, but as you can imagine, we have quite a few more permutations of it because there are so many more positions. Steric number 6 is octahedral, which when you first hear that it is called octahedral, it seems a little weird because 6 things and 8 things are different numbers, but I'm going to show you where that comes from. So octahedral, if you put 6 things around a central atom, the farthest that they can get apart in 3D space is 90 degrees from each other all the way around. So every single one of these positions is 90 degrees from every other position. So even though it looks like this shape has axial and equatorial positions, it doesn't. If I were to take any one of these B's, that look like they're around the middle, rotate my molecule around, it would look exactly the same, right? This angle across the front, that's a 90-degree angle. So 90 degrees for everything. Now, the reason that it's called octahedral is that if I were to connect my top B to the two on the side, right, it makes a little triangle. I can make little triangles all the way around the top. And there's one in the back. And then I can make these little triangles all the way around the bottom. I end up with a shape that has 8 faces. So the faces of the molecule, there are 8 of them, which is why we call it octahedral, but it has 6 things attached in our steric number. Okay. Steric number 6, coordination number 6, octahedral. If we put in one lone pair, so our coordination number is 5, you can put that lone pair in any position you want. So every position is equivalent in octahedral. Now we have a tendency to put it in this bottom spot because it makes the picture a little bit easier to see when we're trying to name this shape. So I'm left with that vertical position opposite the lone pair, and then these 4 that are all in the plane together. Put in my atoms. And the name of this shape is square pyramidal. So it looks like a pyramid that has a square base. For steric number 6, coordination number 4, this is where we do have a special case that I alluded to in the last video. So all of the positions are equal in octahedral, but if I put a lone pair in one spot and I need to add a second lone pair, it will go as far away from the other lone pair as it possibly can. So if I have started putting my lone pair in this bottom position, the second lone pair needs to go on the opposite side of the molecule. And what that leaves me with here is my 4 atoms attached, all in the same plane. They're all 90 degrees away from each other. So the name of this shape is square planar. So all of those atoms are in the same plane. It's just like the trigonal planar that we saw, except that there are 4 things attached, so now it's square planar. Couple more for steric number 6, and then I promise we're almost done. Steric number 6, coordination number 3. Central atom, and we'll put my lone pair somewhere else. So we'll put my lone pair in this position around the middle going back, and that means my second lone pair would go in this spot coming out 180 degrees away from it. And after that, my third lone pair, well, it's going to be in the way of wherever I put it. So it's going to be 90 degrees away from one of these lone pairs in any position. So I'm actually just going to put it in this other position around the middle coming out. So the spots that I haven't filled, the 2 that I've had kind of vertically on the paper, and then this one going back. So B, B, B. Well, this looks pretty similar to something that we saw for steric number 5. If you were to tip this on its side, it looks like the letter T. So this is T-shaped. And the last one will be super fast. Steric number 6, coordination number of 2. If I start with my central atom and let's say put a lone pair going back, The second one is coming out, completely opposite it. Third one, doesn't matter, so we'll put it around the middle going back. So my fourth one has to be coming out 180 degrees away from it. I'm left with these two positions 180 degrees away from each other. So my shape here is linear.